very, very much for this possibility of being with you. Actually, after such an excellent lecture by Marek Niezgódka, it is now come back to the earth and just start thinking about where can we look for our future. Mathematics can live in three states: ground mothering, about funds, about all of those crazy procedures, still without any funding, without any financial support and sustainability in the research. We may face some headaches and other types of mental problems. So perhaps it may be also of some value to just focus on areas where, without sacrificing virtues of mathematics, we can look for our opportunities, and where those attempts can be somehow understood and possibly accepted by policy decision makers, if not here in our country, so at least on the European scale, where the role of mathematics has been quite explicitly acknowledged in a number of studies and surveys prepared over the last decade. And I will start from just a few very short comments. My title refers to time of global digital transformation. Actually, this transformation has already affected the entire academic system to the extent that it goes beyond awareness of many of us. It is not only the directions, but it is also what we all experience these days, sometimes quite curious systems of rewarding, evaluation, and preferences. So I would like to indicate today in my talk that it's meant to be a rather introduction to a possible discussion and set of remarks for all of those assemblies of the Applied Mathematics Committee, Program Committee of this conference, and actually for our entire community. The problem that does exist is that we have not succeeded so far to get a real positioning of mathematics in our academic system. It is just a kind of appendix to other areas of research as far as the proportions in financing are concerned, then the real appreciation that mathematics really deserves. So the fault is unfortunately, in my opinion, not only on the side of politicians, decision makers, but unfortunately, it is very, very heavily based on the attitude within our community. It is lacking kind of concentrated actions of the community that rather prefers to discuss on whether applied mathematics does exist or it's just some addition add-on to that high-level pure mathematics that is so traditionally acknowledged. In the whole world, the role of applied mathematics, applications of mathematical culture, mathematical methods, has been undisputed. Let's think of the consequences of the COVID pandemic with the abrupt acceleration of the transformative developments. We have not used these opportunities as mathematicians to make a very strong impact on the entire change of the situation. And in addition, just let me make a complementary point. Mathematics was always free open. These days, the entire science gets open. The transformation towards what is called open science is becoming a sign of our time. And this is, on one hand, motivated and driven by technological developments, but at the same time, it is the very fact, and here we come to quite close vicinity of the former lecture, to the role that the data and algorithms are playing these days as real game changers. And in this connection, please just note a kind of danger that was for a long time typical attitude among mathematicians. In an attempt to reduce models that were beyond existing formalism, we have often tried to generalize to quite extreme point. And my beloved example, it is the issue of applied mathematical project that was expected to explain why cow is not producing milk. The statement, being a quotation from a quite old paper, says, to start the research, let's consider a spherical cow and try to find features that are most general for further study. This is not the way to proceed. Even though what I by chance found some time ago in Lev Tolstoy, War and Peace novel, the expectation was that starting from the bottom, by taking infinitesimally small units for observation, we can explain everything. We can arrive at the laws of history. But this expectation was, of course, a little bit romantic, and the reality is somehow different. So my talk will be structured in 3 parts, and I start from some remarks on general policy issues related to the position of mathematics and our chances. Well, the European Commission that provides real funds that are interest for mathematicians, at least verbally, has acknowledged the position and the importance of mathematics. And the head of that appropriate division, just in a base a survey of 2020 acknowledged that mathematics is recognized as essential and indispensable for addressing all major challenges everywhere. Still, this very attitude, has proven to be dangerous because mathematics really has been acknowledged to be an addition to all other fields of research, not treated independently. Well, you could see consequences. There were nearly no purely mathematical projects funded within recent framework programs of European Union. Mathematics got the chances only in combination with other areas of science. And so you could find quite long list of projects funded with very high subsidies in application areas where mathematics became a substantial component, but the primary objective was elsewhere. It was not at all mathematical progress, somehow hidden or implicit within projects in so many areas. I will not just list them, but they are pretty obvious. Still, what has been acknowledged also, it was the transdisciplinary impact and character of mathematics everywhere, in all areas of science, including what is quite important these days, including social sciences. And in this connection, the projects where funding was referred explicitly to mathematics included few specific areas. So it was the mathematics in widely understood data science, data application, especially with the help of big data considered. But then there is an area where mathematics can really play a groundbreaking role. It is namely frontier extreme computing technologies, especially in the context of new paradigms in these technologies related to quantum solutions in particular. Just from the other side, to make mathematical achievements widely visible, and this is a comment which maybe should not be ignored. If you look into the general statistics of scholarly communication, the interactions within mathematical community are far below the vast majority of other areas of science, and the effect is that bureaucratic officers tend to prefer those fields which get high visibility and understanding in the general society. So, to make mathematical achievements widely accessible and understandable is really an extreme challenge to our community. And if you look back to Tim Govertz in particular and his fantastic idea of revolutionizing the entire communication paradigm, going into direct, informal extensions of ideas presented on the net, you will find a kind of indication where we have really an opportunity to get and higher, more feedback from the entire world. And last but not least, it is, of course, the impact on innovation. This is the context of introducing the idea of not only applied, but specifically industrial mathematics, and the popularity of this approach has proven quite attractive to decision makers, to the extent that 4 projects referring to industrial relevance of mathematics, the level of funding became significantly higher. And in this connection, again, this conference and our participation in the European network of industrial mathematics may be of some future perspective. So, I have mentioned that frontier computing is one of the areas of special, very special chance for mathematical research. It is not just applications, it's completely new ideas that are needed to break the barriers of scalability in the development of current architectures, accounting for some, not only thousands, but also even millions of computing nodes, and so requiring an appropriate handling, processing of data. The development of solvers, numerical solvers, and their libraries that would ensure high scalability is currently still one of the most demanding and rewarding fields in computer technology and computing. This area is based on breaking the von Neumann sequential concept of computing. It is also a very substantial opportunity for non-deterministic concepts, where the computing processes are organized in a way that is predictive for expected future needs of computational processes, not just follow the complete identification. This is an area which ranges from numerical algebra to especially handling complex network systems and their dynamics. So, combinatorial dynamics is there with the challenges of developing quantitative methods, enabling real processing of high complexity tasks. There is one area, though, this connection, which should not be neglected, and this is the area of energy. If you are aware of those stories about Bitcoin mining and the energy costs behind it, you would understand that energy cost, electricity cost of computing became a non-negligible factor of the feasibility I can only recall from my own experience that already 10 years ago, the monthly cost sent to me as head of one of those centers for electricity bill well exceeded $500,000 monthly. So you should, but this was still all good times that passed away. The today costs are incomparable. So developing algorithms in a way that would also be energy aware is really a challenge which is completely new and until quite recently was not at all accounted for. Then there is this, you have various levels of resolution in handling real applications, real computational applications. So you range from continuum models, so you take this continuum approximation of various complex phenomena, which is actually sometimes the easiest part of the entire story, but then you go down and you come to the atomistic scale of resolution and to the point of existing, still existing capacity of computing, able only to handle, well, in worst case thousands, in best case millions of atoms in a quite accurate way. It makes nothing to do with the scale needed for real applications. But it is still not the issue. The issue is that to make real light solution procedures, you have to combine those two levels. You have to do scaling between micro and macro scales, and this is still a challenge that goes of many ranges of magnitude beyond the current existing technologies. So, in this connection, there is one more challenge. It is the challenge of appropriate approximations that will ensure resilience and correctness still at affordable level and providing reproducibility of the processes on massively parallel architectures. You should be aware of the fact that on massively parallel computer, the assignment of single computing processes is not just a kind of invariant procedure. It is to some extent random, depends on many factors, and actually the effect of it is that you don't get always exactly the same solution, you get approximately similar solutions at various runs of the process. Now, the question is how to ensure an appropriate robustness of the methodology for data-intensive computing. Data-intensive, so based on inflow, high capacity, high velocity inflow of large data to the process and its use. This gives rise to an area which is still in a very early stage of development today. It is the whole area of uncertainty quantification in database high-performance computing. So, to quantify uncertainty in high-performance simulation requires quite a lot of new methodological approaches to provide a reliable assessment of the accuracy granted in this type of computing. You should be aware of the fact that this type of application is, in first row, related to real-time processing and real-time applications. So there is no way to do this a posteriori and quantify the obtained results somehow offline. You have to do this practically online. And I just have found a declaration on the side of European Commission that the research on uncertainty quantification issues for mathematical modeling and optimization is one of the priority direction for funding. Just take it into account. Well, I have mentioned those infrastructures and communication. Its importance for mathematics. A couple of years ago, with the high contribution of Polish groups, an open infrastructure for mathematical applications and data has been set up under the nickname EU DML, Digital Library. Under the link, you can find some results. The project, however, has not been progressed to the level that it would deserve. It is still an area to pursue. Well, is this true that actually by fundamental principle mathematics is open? Well, this is a problem that I have faced once to all of my surprise. Namely, in one of the panels evaluating large-scale projects in applied mathematics applications for industry. This was not in Poland. Unfortunately, until now, I don't recall any opportunity, systematic opportunity of this type here in Poland until now. I'm talking about a program with a funding in the range of 100 million euro, which was offered to mathematicians. And the idea was that the project was for three mathematician and industrialists. Industrial organization granting not only co-contribution, but also declaration of implementing the result. And on that occasion, I have got shocked when a number of projects have got disqualified because of relying on mathematical methods that are closed by patenting. It was the whole area of Monte Carlo approaches in banking, in finances, and I couldn't believe, but I think it was 5 or more projects that got just out of the competition because of involving this type of methodology. So, is mathematics open or not everywhere? We should realize that the Cold War developments, even if not realized, contributed to making quite a number of mathematical methods protected by patents, or in some cases even by some military regulations. We have here Wojtek Witkowski in the audience, so I would be glad to recall that in automatic control theory, Nyquist pattern approximations also belong to this category of protected methods. Their use should be always accepted and acknowledged. Have you realized that? For me, it was another surprise, quite a long time ago. So, my suggestion is that in mathematics, especially, we should be extremely aware of support the concept of patents. It is so easy to legally prevent use of mathematical methods by patent procedures. We perhaps don't realize this stuff, but especially in the US, since that patenting regulation in 1982 that was meant to give support to the use of science, of research results in industry. The effects were not always so direct. And in addition, you can just realize that according to existing rules, what can be protected is not a specific solution, maybe methodology, that is then documented to be potentially of applicability. This has not been widely used in the context of mathematical methods, but in other areas of science, this danger contributed to surprising legal processes. But still, on one hand, the US has been the country where this patenting move became extreme. At the same time, already in 1998, the NSF panel clearly has put mathematical sciences in a position of central importance for the entire research and science. Well, there is a quite interesting quotation from Financial Times of 2008 that documented the scale of use in mathematical methods. Spent a few million pounds on promoting the use of mathematics as a strategic tool, contributed to billions of pounds of value to businesses. This has been elaborated in an extensive way, so we should also not hesitate to refer to this type of argument when applying for quite large-scale mathematical projects. And the fact has been also acknowledged by the World Trade Organization, OECD, and the Global Science Forum, which already in 2008 has produced, I was a happy member of that team, a report on mathematics in the industry. And this report also has indicated and documented the real value of high-level mathematics in practically all areas of social life, of industry and economy. They have proposed the concept of calling mathematics an enabling technology, considering that mathematics is also very unique, horizontal, transdisciplinary area of technological development. So I think again, it is already 15 years. No follow-up has been could be observed in our country. For our policymakers, the recommendation, explicit recommendation of OECD might be of value. Namely, it was that to found interdisciplinary research centers whose mission would be to increase the impact of mathematics in industry. And setting up special positions in industrial mathematics in research institutions, but also in policy-making organizations, equally on national and transnational level. Well, for Poland, what follows for our country? And this is only a short list. It is to complete digital transformation trend and direction in science by an appropriate incorporation of mathematics. At the same time, the harmonization of all areas of public life would gain by using some of mathematical culture, not exact methodology, exact mathematical formalism, but culture. Recognition as enabling technology, of course. And this is very general, but there is concrete behind it. And this is a kind of address and offer to you. Transformation of Polish economy is still in a very early stage. And there is an region whose transformation is of most critical relevance for the entire country because of its industrial weight. This Silesia. Transforming Silesia into smart green region of new technology and science has been somehow already introduced into local policy. Next year, Katowice will be European City of Science for the entire year, with all possible consequences. And programs to be introduced, hopefully, with the use of funds that are temporarily frozen. Huge European funds have been designated to be offered for the transformation of Silesia. And the enormous range of funds are intended to go to science, higher education, and application areas. For specific sectorial fields, environment, healthcare, education, but after all, new energy, transportation, and security. Well, isn't it a chance for the mathematical community to get together and set up a joint project? So to be specific, what is the common denominator of the opportunities? It's data. And not in a way which is complementary, has been introduced by the excellent Dioscuri Max Planck group of or by the research area of combinatorial dynamics by Marek Niezgódka. This is the area of real-time processing. Real-time processing, it's not just characterization of systems, but it is their quantitative dynamics. Qualitative is, of course, an introductory step, but quantitative characterization is really indispensable. And of this, it is the area of decision making. It is the entire area of using imaging data for various types of processing, in decision making, in monitoring, in tracking. It is the area of quantum technology that actually would jeopardize today's cryptography, including blockchain. So it is future, next years already, because this technology is coming. It is not any longer a mirage, it's near reality. As for the problems of challenging value, just those related to epidemic should be really a kind of memento for pushing forward real efforts in analyzing, modeling large multi-scale populations. It is the entire field of biomedicine and biomathematics where precise, dedicated methods open completely new opportunities. Again, it is a problem that the traditional approach, which is usually as first step when you go to continuum resolution level, apply some PDEs or systems, would not be sufficient. You have to go into discrete data-based models and apply, develop new approaches where uncertainty quantification is absolutely the first requirement. But, all of this is related to the concept which is these days most attractive, namely complexity. Even complete knowledge of individual components of a system, in case of real complex situation, would be insufficient for understanding the system as a whole. This remark actually means that microscopic approaches that are so popular in physics, after all, are by far not sufficient for getting understanding of the entire complete system. And this is a research field of very high range of opportunities for mathematicians, because on one hand, you face the geometric or topological complexity of the system domains, which per se introduce substantial difficulties, and forget about any analytic characterization. It is the only way so far to develop appropriate computational simulation approaches that would be really productive. And in this connection, because of the heterogeneous nature of the system's components, it is the necessity of developing hybrid setups. So, combining models with continuous discrete and categorical variables with some highly irregular modeling variables. Again, accuracy and uncertainty are of primary concern. This is a field of research really of frontier nature. Once, for problems over domains that are explicit or implicitly of network character, that represent aggregates of interconnected individual, perhaps even highly regular subdomains, and that are driven by nonlinear exchange mechanisms which do contribute to the development of special structures. Freezing, making focus of a static situation in this type of application is by nearly no relevance. What you need is to get tools, to develop tools that would enable you to describe the nature of such type of transformation. It is the case of systems which change their structure, their properties, physical properties, abruptly, in a continuous way in particular. So this is an area where the current state of the art in mathematical research, despite of seemingly huge literature, is just very, very rare. What is needed, absolutely needed, it is a multi-domain mathematical competence, bridging, analytic, topological, algebraic, and other areas of knowledge. And what is available in literature, almost exclusively, as for today, are some limited steady-state characterizations. It is some results on situations combining very simple, few regular geometries. And after all, it is the single scale setup. No results on dynamics in the case of multi-scale situation. So in the examples of formal lectures, if you just start thinking about additional scale resolution in single nodes of your network and the dynamics that is driven on that local level, but affect non-local properties of the entire system. It is an area where the existing knowledge is extremely sparse. So, to summarize, and I'm again back to my own field of research. For long decades, the most popular approach exploited in the context of such a type of problems was to use models referred to as free or moving boundary problems, which simplify reality to quite large extent. Those approaches usually led to losing any possibility of any insight into intrinsic nature of the processes. So the contradiction between global characterizations and local features, local developments was impossible to overcome. And what is most striking is that the spectacular advances in all of these areas still date back to the early 90s. Then God, the field proved really too difficult, except for physicists. In 2016, for some very special achievements in the context of topological phase transitions, 3 physicists were awarded Nobel Prize. But there are no mathematical advances that would give basis for those theories developed by Toulouse, Aldan, and Kosterlitz. 30 years break. It's time for mathematical advances. It is the most advanced mathematics. And there are quite substantial applied motivations for this type of studies. It is all types of real processes in living organisms and biological systems. It is, as I mentioned, heterogeneous populations, I mentioned, and it is multi-component materials. New materials design, it's a field of real hijacks. It is also the area of operational networks in the context of energy transformation, which is underlying the entire transformation of our public existence. It is transport and it is logistics. Everywhere you need new mathematical contributions based on data-based high, large-scale computing. And so it is the time for intelligent networks to be studied. And my last slide will just refer to the area of some notions where you will see those types of applications in the real real context. It is the area of smart grids, basis for the entire renewable energy generation and the related networks. It is creation of complex ecosystems like smart cities, smart regions, smart organizations, and actually biological systems that are smart by themselves. General smart ecosystem. It is a combination of most advanced analysis, topology, and also algebraic competence but grouped together for computational developments, which are the only way so far for addressing this type of challenges. And I hope that this may be also a real opportunity for this community, because if you look into the map of last 20 years of funding in Poland, you don't find many, and you don't find a single large-scale project that would support this type of activities. And my last sentence is that it was not due to the lack of readiness on the level of decision makers. Some 10 years ago, there was a clear decision to go for. But what was missing? It was the involvement of our community. We were unable to create a real strong task force group that would prepare such program. Thank you.